Okay. I'm not, let's try this. I don't know if my voice is going to make it for the whole thing, but I would like to provide you with a recorded solution and discussion of item 5.2. Like we were just talking about, you should be making notes here and thinking about what's being talked about. The purpose of notes is not to make a verbatim perfect copy of what goes up on the board. It's a way for you to process the information that's coming at you. If you sit there and passively receive it, you're not going to learn any more than you would from watching Gilligan's Island. But if you pass it through your brain, relate it to things you already know, put some of these relations down on paper, or metabolize it in some way, do something with what you're seeing, then you have a chance of making a lasting change in your brain. And knowing how to do physics of electrostatics is not going to be important to you in the future. But if you learn the skills for making lasting changes in your brain, that will be useful every day. Useful not just for profit, but for success and happiness. Okay. So we are going to talk about using Coulomb's law of electrical attraction to reason about electric forces. The proportional form of Coulomb's law is that the force of one charged object on another charged object is proportional to the amount of charge on the first object times the amount of charge on the second object divided by the center-to-center distance between them squared. So in a question like this, it's important to read the text. Rank the magnitude, okay? In other words, how strong of the net electrical forces exerted on little q. So this is the object of interest, this small charged object. What is it in real life? Well, it could be lots of things. You could be doing particle physics with little bits of atoms. You could be doing an engineering project. But try to make some physical picture of what's going on here. The grid is there to, fixed on a grid, the grid is there to hold them in place, I guess, so they don't move while we're talking about the forces. Let's roll back to September and try to do the most basic operation of making a force diagram. You remember how that starts. A dot labeled. Now we're ready to go. What objects are pushing or pulling on the object of interest? Is this object pushing or pulling on the object of interest? Yeah. Now, should we just, since it doesn't say otherwise, let's treat positive Q as though it were a positive charge and see what happens. Is the object with a charge of positive 3 big Q? Is that pushing or pulling on the object of interest? Point, please, in the direction I should draw my arrow. That's right, Charlene. These two objects are repelling each other. So the force of the other charged object on this charged object, is going to be in this direction. Anything else? No. We don't have any information about masses or sizes, so there's no reason to include any other forces. All we want to do is rank the magnitude of the electrical charges, and that's it. What is that force? Don't know. But it's going to be proportional to, so here, this is equal to the total force, and that's going to be proportional to 3 big Q times little q divided by, we need the distance between. We don't know the distance between, but since these grids are all the same scale, we don't need to know exactly what the distance is. Let's just compare them in terms of grid spaces. So that's right, 1, 2, whatevers. Because the distance is squared because of the relationship in Coulomb's law. This is the proportion form, which we use for comparisons. This just says double one of the charges, you double the force. Halve one of the charges, you halve the force. Double the radius, or the distance between, and the force decreases to 1/4 of what it was. So just for fun, let's simplify this. 3 big Q, little q, over 4. Now, is that positive, negative, what? Now, we're talking about magnitude. The question is how hard? Magnitude is like a length. Like the length of the arrow. Always a positive number, but that does not mean a positive charge. It does not mean positive direction, whatever that is. It's just an amount. So really, it doesn't have any sign at all. So the magnitude of the force on this first object is going to be proportional to that quantity there. What is it? I don't know. But let's see if we can compare that to the force exerted on the object of interest in the next question. Once again, let's identify our object of interest. Right here, this object with a charge of the same amount, positive Q. And let's start our force diagram back to the basics. A dot, labeled. And let's identify all the objects that are exerting pushes or pulls on this object. Is this one? You bet. Point in the direction that I should draw the arrow, please. Okay. Some people are pointing like this. Some people are pointing like this. Now, we know why some people are pointing like this. That's because the two objects are repelling each other, and the force of this one on this one is in the opposite direction of the force of this one on this one. That's right, Amber. We're just Autumn. Sorry, I did that on purpose. The joke has taken on a life of its own now. The object of interest is little q, so we don't care about the force on the other one. This is why I've been pestering you for so long to label the forces with two objects. This is the force of positive 9 big Q on little q right here. And once again, since that's the only electrical force, that's going to be equal to the total electrical force on little q, and that is going to be proportional to the quantity from Coulomb's law. One charge times the other charge divided by the distance between them squared. What's one charge? 9q. What's the other charge? Little q. What's the distance between them? 1, 2, 3, 4. So that quantity comes out to be to equal 9/16 big Q, little q. So let's compare now the first two. Which force has a larger magnitude? How do we compare? Now, of course, elementary algebra, which you should expect to screw up when you're doing something more demanding. It comes down to the question of which is bigger, 3/4 or 9/16?
3/4.
Yes, because 3/4 is the same thing as 12/16. Awesome. So far, the first one is bigger. The total magnitude of the electrical force in the first one is bigger than the total magnitude of the electrical force in the second one. Questions? It's about to get more fun. As if that were possible. Object of interest, force diagram, dot, labeled. I'm going to use my superpower of multicolors, and let's break this down. So is this object pushing or pulling on the object of interest? Yup or do. Point in which direction? Didn't ask about moving. Yes. The object, no. One at a time. Back to basics of force diagrams. So, the object I've circled in green, is that pushing or pulling on the object of interest circled in red? Yes. What direction? Yes. What? One at a time. Okay? One at a time. This positively charged object repels the positively charged object of interest. So that's going to be a force in this direction on the object of interest. Let's write it down. This is the force of +3 big Q on little q. Again, with the magic of multiple colors, is the object I circled in blue pushing or pulling on the object of interest? Yup or do. Show the direction of the push or pull of the blue circled object on the object of interest. Point for me, please. This is an attraction. Okay? The object of interest is being pulled in this direction. Right? And this is so easy to get confused about. If you're anything like me, and the only way to succeed in spite of that confusion is to write everything down in excruciating detail. And then double check your work talk to the people around you, look for any place that you differ. So this is a repulsion. This is an attraction. Just to keep straight in our heads what's happening here. Now, we've drawn all the arrows on our force diagram. How do you combine the arrows on a force diagram? You guys got a picture over here too.
What does that say?
Well, the total, let's do it this way. The total force on the object of interest is going to be the result of combining both of these arrows, right? If I combine them visually, it's going to be like this, right? Now, it's totally a force diagram. So now that we've identified all the electric forces, it's gravy. Because all we have to do is treat these arrows like we've treated arrows on every other force diagram since October. Okay? Now, the magnitude of this force is equal to the length of this arrow. How long is that? How long is that combined arrow? Well, the magnitude of the green arrow is going to be proportional to the absolute value of one charge times the absolute value of the other charge times the divided by the distance between them squared. Why are we putting the absolute values around it now when we ignored it before? Now it's more complicated. It's good to remind ourselves. So what are the two charges? Negative, positive, 3 big Q, little q. Distance, 1, 2, 2 squared. And that's going to be proportional to the absolute value of that. Comes out again, 3/4 big Q, little q. Let's do the magnitude of the attraction. The magnitude of that force is going to be, again, one charge times the other charge, divided by the distance between them squared, absolute value of. And that equals so we have the length of both of these arrows. Okay. Why is neither of those negative? Because we're going to get the magnitude of the force from the Coulomb expression. The magnitude is like the length of the arrow. And it's not positive, it has no sign. In one way of thinking about it. So the length of those two arrows combined is 3/4 plus 3/4.
3/4 plus 3/4?
6 quarters.
6/4. Absolutely. So so let's go right ahead and simplify that to 3/2. Big Q, little q. Take a minute and think this through. Lots of people at this point, from brain fatigue, after having added the fractions together to get 3/2, will then try to add the q's together, and that ain't how it goes. 3/4 pizza plus 3/4 pizza 1.5 pizza. Don't freak out. Having come all this way, stay chill for the last stretch.
So 3 over 2 big Q little Q is how long the whole line is?
That is the length of the total electrical force on the object here. Now, is that less or more than the previous ones? Mo. Right? That total force, whatever it is greater than either of the previous two examples. 9/16 or 3/4. Same drill. Let's consider the last one. Object of interest. Start our force diagram. Consider the object exerting pushes or pulls on this. The object circled in green, these are two positively charged objects, so they're repelling each other. So the force of positive big Q on little q is going to be in this direction. Circle this object in blue, that's also repelling the positively charged object of interest. And just from looking at it now, we're feeling a little more confident. We might want to draw that arrow a little longer and label this as the force of plus 3 big Q on little q. Now, how do we combine two arrows pointed in the opposite directions? You know that the result of combining these forces is going to be something smaller, because the total electrical force here is going to be the product of combining this large force in this direction with this smaller force in this direction. So it's going to end up as this. Remember the trick we use to add these up in an idiot-proof way. For me, the only way that always works is the idiot-proof way. So this is another time not to skip and try to do shortcuts. Let's do our old trick where we arbitrarily choose one direction of the back and forth and call it positive. Because another use, remember we listed a million things to do with these two symbols. One use of them is to keep track of position on an axis. And direction's a better word. Like when you put your axis wherever you want and say this direction's positive, this direction's negative. So with our completely arbitrary choice, that one becomes positive, this one becomes negative. The sum of the forces is always the result of adding. So we're going to be adding the negative force, the negative length of this arrow, I'm going to add that to the positive force of this arrow. So the magnitude of this force, big Q, little q over 1 squared. In fact, just big Q, little q. The magnitude of this force, also separated, well, I got them backwards, but you're okay. This is also 3 big Q, little q over 1 squared, or just 3 big Q, little q. Those are lengths of arrows. They have no sign. It's just magnitude. So when we add the negative magnitude let me stick with my colors here. Negative big Q little q plus the positive magnitude of the repulsion
What?
total magnitude. Now, none of the algebra here is stuff that you haven't already been doing for 2 or 3 years. But applying it to the physical reasoning about these charged objects is, without doubt, a challenge. So, to summarize the story so far, here's the total magnitude, total magnitude, total magnitude, total magnitude. So the ranking would be, this one's the strongest, followed by this one, followed by the first one, and this one is the least strong.
It makes sense.
Okay, like anything, this is not going to become permanently part of you until you do some yourself. So I'm going to stop the recording here.